Dear students, myself Shashikala, Department of Physics. Welcome to first B.Sc. In your first semester, you are going to study 4 units. The syllabus for first B.Sc Physics is, there are 4 units. First unit is Mechanics 1, second unit Mechanics Part 2, third one is Thermal Physics, fourth one is Physics of Low Temperature and Pressure. These are the 4 units which you are going to study in your first semester physics. And the examination pattern, the physics paper, it has got total 150 marks. There, 100 marks for theory, 50 marks for practicals. In theory, the SEM exam is out of 80, 20 marks internal assessment, total 100. Then practical part, 30 marks for your experiment, the actual experiment what you are going to conduct or perform in the examination. 10 marks for record, your class record, 10 marks for internal assessment, total 150. This is your examination pattern. And today I am going to start the first chapter of the first unit. First unit is Mechanics 1. In that, the first chapter is Vector Calculus. It is Introduction to Vectors. You have studied about the physical quantities and the classification of physical quantities in your PU classes. I think in your first B.Sc, you have studied about the physical quantities. What are physical quantities? The quantities which can be measured are called the physical quantities. And the physical quantities are classified into 2 groups as scalar quantities and vector quantities. What are scalar quantities? The physical quantities having only magnitude are called as scalar quantities. For example, mass, distance moved by a particle or a body, volume, density, pressure, magnetic flux, electric flux, electric potential, all these are scalar quantities. They possess only magnitude. The specific direction is not mentioned. These are scalar quantities. Vectors or the vector quantities, the physical quantities having both magnitude and direction are called the vector quantities. They are having both magnitude and direction. For example, velocity, displacement, acceleration, force, momentum, torque, angular momentum, electric intensity, magnetic intensity. All these are scalar quantities. These are physical quantities. What are physical quantities? Which can be measured. These are classified into 2 groups as scalars and vectors. A vector quantity has got both magnitude and direction, and usually we represent a vector quantity by a straight line with an arrowhead. Length of the line indicates the magnitude and arrowhead shows the direction. This is about the graphical representation of a vector. The vector quantities, the operations in vector quantities, operations are vector addition, vector subtraction and vector multiplication. How the vector quantities are added? It is vector addition. Suppose you have 2 vectors in general, say represented by the letters A vector and B vector. These are 2 vector quantities. Then we represent these 2 vectors by the straight lines. And if it is to be added, if the 2 vectors are to be added, it is nothing but A vector plus B vector. How the 2 vector quantities are added? Here we apply the triangle law of addition of vectors. There we represent the vectors by the 2 sides of a triangle. See, one vector say OA represents the line side OA represents, or say OP represents the vector A. Then suppose PQ represents, the line PQ represents the vector B, then OQ represents the vector C, nothing but A vector plus B vector. This is how 2 vectors are added. This is vector addition. Triangle law of addition of vectors. What it says, if 2 vectors are represented by the 2 adjacent sides of a triangle taken in order, the 2 sides of a triangle taken in order, see OP, PQ, they are taken in order, then the third side represents A vector plus B vector, in opposite order. See, the two are A vector, B vector represented in this way. They are taken in order, whereas C is in the opposite direction. This is vector addition. How the two vectors are subtracted? Vector subtraction is A vector minus B vector. It's again another vector, say C vector. How the two vectors are subtracted? See here, the vector A represented by the side OP, the line OP. B vector represented by PQ. So that minus B vector, it is nothing but it's represented in this direction. Opposite to B vector, nothing but minus B vector. Then this side OQ represents the vector C, nothing but A vector minus B vector. This is vector subtraction. Now let us consider the next operation, multiplication of the vectors. Suppose we have two vectors, A vector and B vector. How these two vectors, they can be multiplied in two different ways. They are scalar product of those two vectors and also vector product of two vectors. The vector multiplication has got two types. One is scalar product of two vectors, vector product of two vectors. What is scalar product of two vectors? Here we have a vector A. We have two vectors. So we have two vectors, A vector and B vector. Then their scalar product is defined as A vector dot B vector. We put a dot between, indicates the scalar product of those two vectors, also called dot product. Defined as the product of magnitudes of the two vectors and cosine of the angle between the two. Say, suppose we have two vectors, A vector and B vector, inclined to each other by an angle say theta. Then the scalar product of these two is given by AB cos theta, where theta lies between, it is 0 and pi. Theta lies between 0 and pi. This is the scalar product, and scalar product of vectors, any two vectors, is always a scalar. It is always a scalar. This term AB cos theta does not contain any quantity indicating the direction, so it is always a scalar. Scalar product is always a scalar. Here AB are, the A and B are magnitudes of A vector and B vector. Usually we denote the magnitudes as the magnitude of the vector A, denoted by symbol mod A vector, or simply the letter A indicates the magnitude. Similarly, modulus B vector, simply the letter B indicates the magnitude. Magnitudes are scalars. It's about the scalar product of two vectors. Suppose the given vectors A and B are represented in three-dimensional Cartesian coordinate system. You are knowing about the three-dimensional Cartesian coordinate system. The three axes at right angles to each other, OX, OY and OZ. O is the origin. Then, if these vectors are represented by the represented three-dimensional Cartesian coordinate system in terms of their components, the vectors, they got three components. The vector A is A1 I cap plus A2 j cap plus A3 k cap. Here A1, A2, A3 are the components of A along X, Y and Z directions respectively. A1, A2, A3 are the components along X, Y and Z directions, whereas I cap, J cap, K cap are the unit vectors along X, Y, Z directions. I cap, J cap, K cap, they indicate the unit vectors along X, Y, Z directions. What a unit vector is? A vector having magnitude 1 is called a unit vector. So I cap, J cap, K cap are the vectors having magnitude 1 and their directions are along X, Y and Z respectively. This is the conventional node considered. I, J, K are taken as a unit vectors along X, Y, Z directions respectively. In a similar manner, we represent another vector B in terms of its components as B1 I cap, B2 J cap, B3 K cap. B1, B2, B3 are the components of B along x, y, z directions respectively. Now let us find out their dot product or the scalar product. What's the dot product? A vector dot B vector. By definition it is this term dot this term. I have not written those things here. A vector dot B vector is nothing but this term dot this term. So you have to multiply, take the dot product between the components also. Here we take the dot product between the components. And one thing you have to remember here, the dot products, say I dot j, j dot k, I dot k, or k dot I, k dot j, or j dot I. All these products, they are always equal to 0. You know the reason why is ij or jk or ik, the vectors at right angles to each other, ij, jk or ki, they are the vectors at right angles to each other, so that angle between them theta is 90 and therefore cos theta here 0, cos 90 sin 0 equal to cos 90 0, therefore these dot product are always equal to 0. Whereas I dot I, j dot j, k dot k, the dot product between these vectors always equal to 1, because here angle between I and the same I, it is 0, cos 0 is 1, therefore this dot product becomes 1. By considering this, if you take the dot product of these two vectors, then see here we take the product of the components a1 b1 I dot I is 1, so a1 b1 remains there. We get a1 b1. Next is a1 b2 I dot j 0, that becomes 0. a1 b3 I dot k 0. Next a2 b1 j dot I 0. a2 b2 j dot j, that remains. It becomes a2 b2 into 1. a3 this one again 0. Now from a3 to this, a3 b1 ki 0. a3 b2 k dot j dot k cap dot j cap 0. a3 b3 k cap dot k cap remains. So that we get the dot product as a1 b1 plus a2 b2 plus a3 b3, and it does not, this expression does not contain any unit vector, indicating that this product is a scalar. This is a dot product of two vectors in terms of the components is obtained. A vector dot b vector is given by this, no unit vectors there in the expression, so it is a scalar. Dot product is always a scalar. If you take the dot product between a and a itself, a vector dot a vector, in that case what you get? a1 square, a dot a is a1 square plus a2 square plus a3 square, or a dot a is aa cos theta, aa cos theta, theta is 0, that becomes aa cos aa into 1 a square equal to this, or from this we get a as square root of a1 square plus a2 square plus a3 square. This is the magnitude of the vector a. What about magnitude of b? It will be root of b1 square plus b2 square plus b3 square. This is how you can find out the magnitudes of any vector in general using this expression. Example for scalar product of any two vectors is work done and electric flux. These are the examples for the scalar product. See, work done we defined as the product of the force and displacement. F is the force, R is the displacement of the particle, and when the force F is applied on it. In that case, work done is given by F vector dot R vector, nothing but F R cos theta, where this F cos theta is the component of the force in the direction of displacement. Suppose a force applied on the particle. Particle is here, the force applied in this direction, say F is applied. Suppose the particle gets displaced in this direction, making an angle theta. This is the direction of force. So that the component of F vector along the direction is F cos theta. So that work done is product of F cos theta and R. Nothing but F vector dot R vector, always a scalar. Work is a scalar, you know it already. Similarly, electric flux, it is also a scalar. It is defined as dot product of electric intensity and area. It is EDS cos theta is a scalar. This is about scalar product of two vectors. Scalar product always a scalar. So you have studied these things in your PSC, just refreshing the things, that's all. Nothing special here, you know these things already. Next is vector product of vectors. One more type of product of vectors, multiplication of vectors, it is vector product, also called as cross product. Also called cross product. Cross product or vector product. We define it as A vector cross B vector. Given by product of magnitudes of the vectors and sign of the angle between the two vectors with a unit vector n cap. Thus, it indicates that where theta lies between 0 and pi, so that A cross B vector is AB sin theta n cap indicates that the vector product or the cross product is always a vector. It is always a vector. Now in terms of components, how to get the cross product? Here already the vectors AB are written in terms of their components. Now cross product. To get the cross product or the vector product, you have to consider the determinants. This one is also, you know, this method, how to find the product. Here I, J, K are taken in one row, A1, A2, A3 next row, B1, B2, B3 next row. Then you know the method, how to take this product. First row, first column eliminated, I cap A2, B3 minus A3, B2 minus J cap into A1, B3 minus A3, B1 plus K cap into A1, B2 minus A2, B1. And this is the cross product of two vectors. It's always a vector because it contains I, J, K, the directions. So that's what both magnitude direction, it is a vector. Cross product of two vectors is always a vector. Example, angular momentum and torque. What's angular momentum? Moment of momentum of a particle. When a particle is in circular motion, it possesses momentum, that is the angular momentum, also defined as moment of momentum. Angular momentum N is the cross product of R vector and P vector. R is the position vector, P is the momentum vector. What is P? Linear momentum. P vector is M into B vector, and cross product of the two is nothing but angular momentum. Moment of momentum expression. You might be remember that MVR is the expression for the angular momentum. Tau, the torque. The torque is the one, it's a vector quantity. The torque is one which produces rotational effect on a body. Whenever a force applied, the torque is nothing but the rotational effect produced in that body. It is torque, it's also a vector, cross product of force and the displacement. This is about scalar product and vector product of two vectors. Next is derivative of a vector. Suppose we have a vector which is the function of a scalar. Suppose you have a vector which is a function of a scalar. A vector in general is a vector function of the scalar, say t. T usually represents the time. Let A be the function of the time. Time is a scalar quantity. Then in that case, the derivative of that vector is nothing but dA vector by dt. Suppose there is a very small change in the vector A, say delta A. In a small time, say delta t, then limit delta A by delta t with delta t tending to 0 is called as the derivative dA vector by dt. The differential value of that A vector with respect to t, with respect to that scalar. Differentiation of A with respect to scalar t, it is called derivative of A. So here A is the function of the scalar quantity t. If you differentiate, we write A in terms of their components like this. So d by dt of the vector A in terms of its components. Here it is nothing but differentiation of the component A1, that of A2, that of A3. So we get dA1 by dt I cap plus dA2 by dt j cap plus dA3 by dt k cap. And here derivative of A1 denoted by the symbol dot, A1 with the dot, A1 dot I cap plus A2 dot j cap plus A3 dot k cap. The dot indicates the first derivative of that quantity. So first derivative of A1, A1 dot, that of A2, A2 dot, that of A3, A3 dot, this. The derivative of the vector A is given by this. Then magnitude of the derivative of the given vector. Mod dA vector by dt, it's nothing but dA by dt is equal to square root of a1 dot square plus a2 dot square plus a3 dot square. This is about the derivative of a vector. Then, so in mechanics, we come across the quantities like velocity, acceleration. Whenever a particle is in straight line motion, there we define the displacement, velocity, the vector quantities, displacement, velocity, acceleration, force, etc. What is velocity? Rate of change of displacement is called velocity. Usually, displacement of a particle represented by the vector r is, and velocity denoted by symbol v, acceleration by the letter a. And we define velocity as dr vector by dt. If the displacement vector is the function of time, as the position changes with the time, the velocity, the particle acquires velocity, defined as dr vector by dt. And acceleration is defined as dv vector by dt. These are the derivatives, the quantities we come across in mechanics when the particle is in straight line motion. I think with this I stop here. Let us continue the next class with some other topic. Thank you.